What's your earliest memory? For most people, it's something from age 3 or 4. A birthday party, a family trip, a feeling. Before that, nothing. A blank. Your first steps, your first words, your first birthday, the faces that smiled at you every day for years, all gone. This isn't a quirk of aging. Your brain systematically erased these memories as part of its own development. It's called childhood amnesia, and it happens to every human being on Earth. The question is, why would your brain delete the first years of the most important learning period of your life? Long-term episodic memories, memories of specific events with a time, place, and narrative, are formed primarily by the hippocampus. This seahorse-shaped structure deep in the temporal lobe binds together the separate elements of an experience, what you saw, heard, felt, and where you were, into a single retrievable memory. The problem: the hippocampus isn't fully developed at birth. The dentate gyrus, a critical subregion of the hippocampus involved in forming new memories, doesn't reach the functional maturity needed to hold long-term memories until approximately age 3 to 4. Before that, the hardware for storing episodic memories simply isn't online. You experienced your first years, you just couldn't file them properly. Here's where it gets fascinating. Even when the hippocampus is forming memories in early childhood, those memories are being actively overwritten. The infant brain undergoes rapid neurogenesis, the production of new neurons, at a rate far exceeding the adult brain. In the hippocampus specifically, new neurons are integrated into existing circuits constantly. When a new neuron is added to a circuit that holds a memory, it disrupts the pattern of connections that encoded that memory. The memory degrades. Research by Paul Frankland and colleagues showed that increasing neurogenesis in adult mice caused them to forget previously learned information. Decreasing neurogenesis in infant mice actually improved their memory retention. The very process that builds your brain also destroys the memories stored in it. A baby's brain is wildly overconnected. By age 2, a child has roughly twice as many synaptic connections as an adult, approximately 1 quadrillion synapses. This is deliberate. The brain overproduces connections, then prunes the ones that aren't reinforced by experience. Use it or lose it at the neural level. This pruning is essential. It's what allows the brain to specialize and become efficient. But it comes at a cost. Memories that were encoded in the pre-pruning neural architecture may lose their structural support when the connections that held them are eliminated. The brain is remodeling itself so aggressively in the first few years that the memories stored in the old architecture don't survive the renovation. There's another dimension to childhood amnesia: language. Most episodic memories in adults are encoded with a narrative structure, a story you can tell yourself about what happened. Before language development, infants experience the world in a pre-verbal mode. They can form emotional associations and procedural memories. They learn to walk, recognize faces, and develop attachments. But they can't encode events as retrievable narratives. Once language develops, the brain shifts to a language-dependent memory system, and many scientists believe pre-verbal memories become stranded because they can't be translated into this new format. It's like having files saved in a format your new operating system can no longer access. A critical misconception: childhood amnesia doesn't mean babies can't form memories. They absolutely can. 6-month-olds can remember specific events for at least 24 hours. 9-month-olds can remember actions demonstrated to them a month earlier. 2-year-olds can recall events from months ago and describe them once they have language. The memories form, they just don't persist. Longitudinal studies have tracked children's memories over time. A 3-year-old can describe a trip to Disneyland vividly. By age 7, the memory has faded. By age 10, it's usually gone, replaced by family stories and photographs that create false familiarity. The experience was real, the memory was temporary. In a 2018 study published in Psychological Science, researchers surveyed over 6,600 people about their earliest memories. Nearly 40% reported memories from age 2 or younger, and 13% claimed memories from age 1 or younger. This is highly unlikely given what we know about hippocampal development. These memories are almost certainly fictional, constructed later from family stories, photographs, and imagination, then experienced as genuine memories. The brain doesn't distinguish between a true memory and a convincingly constructed one. The feeling of remembering is identical. Your earliest memory is most likely a story you were told so many times that your brain built a scene around it and filed it as a personal experience. Why would evolution design a system that erases early memories? One hypothesis: the function of early brain development isn't to remember, it's to learn. The massive neurogenesis and synaptic pruning of early childhood are building the brain's foundational architecture: language circuits, motor control, social cognition, emotional regulation. These are implicit systems that don't require episodic memories to function. You learn to walk, but you don't need to remember the specific day you took your first step for the skill to work. The memories were scaffolding. Once the structure is built, the scaffolding comes down. Your brain chose capability over memory. And it was probably the right trade. Your first word, your first step, the first time you recognized your own name, all of it, experienced and erased by a brain rebuilding itself so aggressively that the memories couldn't survive the construction. You were there, you just don't remember, and that might be the price of becoming who you are.
Science Untold. See you next time.